For the second part of this lecture set, we'll be talking about the reliability of measurements. So just a reminder, please remember that reliability and validity are not the same thing. Reliability refers to how consistent or regular a measurement is, versus validity oftentimes refers to either how accurately a variable is operationalized or how accurately it allows for generalization. And then we also talked about internal validity also previous class. So just remember that validity is actually much more far-reaching and nuanced than reliability, and that they're oftentimes conflated in common day language, but that they have very different interpretations here when we're using them scientifically. Now, a little bit about correlations before we get into the three types of reliability that we'll talk about in this chapter. So correlations are probably the most common way of evaluating reliability. Before you get into the correlations in your textbook, you will notice that the author spends some time talking about using scatter plots to evaluate reliabilities. These diagrams here are ultimately scatter plots. I am not going to spend time really talking about scatter plots being used to evaluate reliability, because overwhelmingly in the literature and what you would be required to report will be correlations of some kind, and not actually the scatter plots themselves, though it can be handy to learn how to read them. To see really how inaccurate, I suppose, human beings are looking at this type of data that you can see here on these scatter plots presented right here, and how, well, not so great we are at evaluating the numerical magnitude, you can go to guessthecorrelation.com. It gives you a fun, very old DOS-looking video game. I'm not sure how many of you actually know what DOS is anymore, but that doesn't really matter. It kind of looks like an arcade game. It will pop up with these types of images, and your goal is to guess the actual numerical value. If you're outside the sort of range of guessing, you lose lives, and if you are really close, you get lives. And it can be kind of entertaining if you're that way inclined. But it's a good way to show that we're not the most accurate at evaluating actual numerical magnitude by looking at such graphs. The way these work, though, and this is ultimately the basis of how correlations work, you have two different measurements, in this case y and x, and one is evaluating a measurement on both of these. So each dot represents a single individual, whether that is a human being, a bacterium, a light bulb, it doesn't really matter. And it has a measurement that exists on both metrics. So for this dot right here, there's maybe an x value of about 2.5 along with a y value of 1. And this kind of then is true for all of these individuals. This correlation corresponds to a correlation of 0.56. We'll talk about the bounds in just a moment, even though hopefully that will just be review for you. Here you can see that the more and more your scatter plot looks like a cloud of gnats, just fully distributed across all quadrants of the available space, the more the correlation coefficient is going to be near 0. The closer it is to one consistent line, the closer it is going to be to 1 or -1. What will determine the sign of it is the direction of the line that it is forming. When you have something that is increasing on both values together, where you have a line going from the bottom left to the top right, this will be a positive correlation. As one increases, so too does the other, and as one decreases, so too does the other. Here you can see the only example out of these four of a negative correlation. Even though it's not that strong, you can see that it is forming somewhat of a line moving downwards from the top left to the bottom right. This would be a sign of a negative correlation. Now, a negative correlation is not inherently weaker than a positive correlation. All the positive and negative are indicating in correlations is the direction of the relationship, not the magnitude itself. So here you can see what ultimately classifies or constitutes a negative relationship in this case is as one variable increases, so as values on x increase, we see that values on the other decrease. So as x is going higher, you see that values of y are coming down. And the reverse happens as well. As x values are decreasing, values of y are increasing. And note that you can say that in either direction, right? As y is increasing, x is decreasing, or as x is increasing, y is decreasing. It doesn't matter in which direction you say it, it's ultimately true in both directions. So some specifics about correlations. You will find that they are bounded between -1 and 1. What this means is you cannot have a correlation coefficient that is outside of this range. it is not possible to have a correlation coefficient that is beyond -1 or +1. And if you ever see it somewhere, someone has made a calculation error in their work. Now you'll often see it abbreviated as a small italicized r. This is for one type of correlation. It is the most commonly found form, even though you will oftentimes see other symbols because they are actually several different types of correlations that you can calculate. But a lot of this is ultimately determined by the type of measurement you're using and whether that data is normally distributed or not. Now again, please remember, the sign has no bearing on the strength of a relationship here. So moving into the reliabilities, the first two that we'll talk about are somewhat straightforward. The first being test-retest reliability, which just refers to the consistency of results every time a measure is used. So this could be, I measure how tall a person is today, and then I measure how tall they are in a week. And hopefully they should be about the same height at both of those measurements, because people don't really change in height that much over the course of a week, especially when they're adults. In such a case where the measurement at time 1 is very close to the measurements at time 2, we would say that that test has high test-retest reliability. Whereas if something tends to fluctuate a lot, we would not say that it is high test-retest reliability. Now please note that or an example to illustrate what is not sort of found under this is if I measure the temperature today and it's 86 degrees Fahrenheit, and then I measure the temperature tomorrow and it's 72 degrees Fahrenheit, and then I measure the day after and it's only 65, and then I measure on the fourth day and it's 87 again, that's not a sign of low test-retest reliability, because it could be that the world outside is actually changing. But if I was to measure the temperature on 5 different days where the weather service reported that it is exactly 72 degrees where I live and am measuring, and my thermometer on all of those days gave me different readings, that would be a sign of low test-retest reliability. But if that thermometer was accurately and reliably reflecting the changes in temperature outside, then that would still have high test-retest reliability, even if the temperature outside was in fact changing. Now please note, no matter how simple your measurement tool is, it will never perfectly match across all data points. So even if I was to measure everybody's height right now and then measure everybody's height in 10 minutes, the heights really probably haven't changed much, but they won't match perfectly. This is largely due to ultimately what we refer to as measurement error, but it could be that maybe I get a little bit tired, I round down just because I don't want to look at all the little tick marks between 2-inch sort of tags on this measurement item that I'm using. It could even be that the measurement tape I have expands and contracts at different rates based on the temperature that it is outside. And if I have a class that is 150 people, it might be late evening by the time I get to measuring everybody by the second time, and maybe my measuring tape has contracted a little bit, and so people appear taller now at the second point. A lot of this stuff actually creeps into the way that we measure things, because we oftentimes don't look at all this subtly nuanced things. And for many of them, it doesn't really matter that much. But please note that it's next to impossible to ever evaluate test-retest reliability to a level that is perfect. There'll almost always be some error. The way in which this is evaluated is much like those scatter plots I showed you on the previous page. You would have ultimately each data point that would represent the measurement at both times. So on one axis, you would plot the measurement at time 1, and at the second axis, you would plot the measurement of time 2. And ideally, the closer this formed to a straight line, the higher the test-retest reliability. Or in other words, the closer the correlation coefficient is to 1, the better the test-retest reliability. Versus if the correlation coefficient is close to 0, then the test-retest reliability is pretty horrible. Something for you to think about is, would you ever have a good test-retest reliability if the correlation coefficient was negative or close to -1, let's say? Moving on, we have inter-rater reliability. This is similar, except instead of testing across time using the same measure, you have judges or raters or evaluators who are looking and quantifying behaviors oftentimes, and this is to evaluate how closely different people's rating of the same individual or behavior actually match each other. So a case where this comes up a lot is when people are doing observational studies. So imagine you and your friend are part of a developmental psychology lab, and you have been tasked with evaluating how many violent behaviors take place at a preschool during recess. So you and your friend could go now and you would have a little notepad, let's say, where you kept track of what violent behaviors you saw. Now, what you could do to evaluate inter-rater reliability is look at how much both of your two sets of ratings agree. If both of you saw a kid named John push another kid, Mary, let's say, and you both marked that as a violent behavior, we would say a high degree of agreement. Whereas if one of you sees someone kind of take a pen from somebody else and one rates that as an aggressive behavior while the other does not, that will tend to lower inter-rater reliability. But please note also, right, that we won't do this on just one behavior itself. Oftentimes this is over an entire set of behaviors that the two judges are ultimately reporting on. And I mean, it can be more than two judges as well. It is relatively difficult to get very high inter-rater reliability, right? You're oftentimes not going to see a correlation coefficient here close to 1, and the field has different opinions of what counts as adequate inter-rater reliability. Oftentimes, you want something at least beyond a correlation coefficient of 0.6, but like I said, a lot of that is going to depend on the particular field in which that research is being conducted and the specific focus of the research itself. Again, this can be evaluated using correlations, and in this time, instead of putting time 1 and time 2 for the same measurement on your axes, you just put ratings of one judge on one axis and another judge on the other. If ever you have multiple coders, there are ways to evaluate correlations with beyond just two variables. Last but not least, we have internal consistency or reliability. These two things can be used interchangeably. Now, this is used a lot in survey research, especially, or any type of questionnaire development, if you're at least good researchers. Now, this is a measure of how the items in a measure the same type of thing. The degree to which they're all measuring the same type of thing, the higher the internal consistency or reliability. And this should not be dependent on the way that these questions are phrased or structured. Now, the way this is evaluated is no longer using a direct pure correlation, but through something called Cronbach's alpha. And Cronbach's alpha is, in a way, just a very fancy form of a correlational structure, test maybe. What it's actually doing is it's evaluating the individual pairwise correlations of all the individual items. So of these 5 items here, for example, it would evaluate how item 1 is correlated to item 2 and item 3 and item 4 and item 5, and how item 2 is then in return correlated to 1, 3, 4, and 5, and item 3 to 1, 2, 4, and 5, and so on and so forth. And then ultimately what Cronbach's alpha is kind of an average of all of those intercorrelations. And so the higher that Cronbach's alpha, the closer to 1 it is, the more that indicates that all of the items on your measure are all indexing the same type of thing. The lower that is, the more sort of haphazard those items are, and they're not being interpreted in the same way by whoever is your respondent. Please note that this is unbelievably important when you are reading this type of information. If you are reading research in which they're using scales and questionnaires, and those scales and questionnaires have reliability ratings in terms of Cronbach's alpha of lower than 0.7, it does not actually make sense to take averages and sums of those data because they're not actually measuring the same thing, and thus collapsing them and performing statistical analyses on them is not actually meaningful. It is not truly representing the underlying constructs that one is claiming it to be. So if you see measures where they're either not reporting Cronbach's alpha or it is very low, let's say below 0.6, I would be very careful interpreting that data. Now, to use these 5 items, these are a well-being scale. The 5 items are: in most ways, my life is close to ideal. The conditions of my life are excellent. I'm fond of polka dots. I'm a good swimmer. And if I could live my life over, I would change almost nothing. So in the dashes, one could put 1 through 5, let's say, of ratings. You could be filling out bubbles if you were doing this on a computer. And here you can see that items 1, 2, and 5 do seem to fit with some kind of subjective well-being measurement. Whereas how much you like polka dots and whether or not you're a good swimmer are not actually highly related to your own subjective well-being. I can imagine people who love polka dots who are doing really well and others who are not doing so well. In this case, if you were to put all 5 of these items together and run Cronbach's alpha, chances are it would not be very high. But you could now remove items 3 and 4 from this set and then run it again, and chances are it would be much higher. Now, this is actually one of the ways in which survey development takes place. A good survey design flow will, even let's say if you end up with a questionnaire that's going to have 10 items, ideally you start with far more than just those 10, and this is one of the processes by which you can whittle those down. We also use something called factor analysis, which you would have to wait for a more advanced statistical class to study. I mean, you could look it up if you wanted, but that's extra work and, well, yeah. Okay. Before we conclude on this though, there are some cases where we will have these types of unrelated items. So the first is of course reverse coding or reverse worded items, which technically should not interfere with Cronbach's alpha so long as they're recoded correctly. And this just means that you add the statement kind of in reverse. So if I was taking the second one, for example, of the conditions in my life are excellent, I could go from disagree to agree. And to reverse code this, I could say something like, the conditions in my life are appalling or horrible, in which case I should answer it in a similar way, just reversed. And this is oftentimes used to sort of make sure that people are actually paying attention to their questions, because it's a way you can catch people from just sort of selecting I agree all the way down. In a related form, we have something that are called attention checks. And these are these types of questions like I'm fond of polka dots or I'm a good swimmer. Because what you can do here is evaluate the reliability, leaving in these attention checks. And anyone who has a very high reliability when the attention checks are inside, chances are they were not paying attention, because they should not be a high degree of agreement between the well-being questions and how much you like polka dots and are a good swimmer. So you will tend to find these types of attention checks in some types of scales, but it depends on who is developing those scales and whether they wanted to put them in. Please note that if you are using an established measure, you cannot just stick attention checks inside, because that will invalidate the measure itself, because it was designed in a specific way, and you cannot just willy-nilly change it if you feel like it.